Good day, I'm J Wildberger, and in today's video we're going to be looking at how to convert Boolean functions to Boolean expressions. And we're going to look at the standard procedure that's taught in Boolean algebra-oriented courses, which involves two different kind of approaches. One involving a sum of products, and the other involving a product of sums. And we're going to see that with the Algebra of Boole approach, we can circumvent the distinction here, that neither of these becomes really the primary tool, that we're able to move beyond both of them and the distinction kind of disappears. And along the way we're going to see a little bit of pleasant algebra also. That's kind of interesting. So we're going to work through specific examples so you'll see this dichotomy take place. So here are three variables, a, b, and c, and here is a Boolean function f depending on the usual 8 inputs. Now, one expression for f is as a sum of products, and that looks like this. This is obtained by looking at those rows that correspond to ones. So basically we're saying, when is f equal to 1? F is equal to 1 when either this condition is satisfied, or this condition is satisfied, or this condition is satisfied, or this condition is satisfied. Okay, so this condition here corresponds to a bar, b bar, c bar. The bar is because there's zeros here. The next one here corresponds to a bar, b bar, c, corresponding to the 0, and the 1, and so on. Okay, so that's one way of describing this Boolean function f. Another way is to concentrate on the zeros, to say, okay, this function f is going to be 1 when this is not satisfied, and this is not satisfied, and this is not satisfied, and this is not satisfied. So we have 4 conditions corresponding to the zeros, but now they're connected with an and, so they're represented by a product. And each of these things is capturing when this is not happening. So this 0 here will not happen when a is 1, or when b is 0, or when c is 1. So a, circle sum b bar, circle sum c, corresponds to when this condition is not going to be satisfied. Similarly, this one corresponds to this not being satisfied, this corresponds to this not being satisfied, this corresponds to this not being satisfied. So we have these two ways of expressing f as a sum of products, essentially correlating to the ones in the list of values, and as a product of sums, essentially corresponding to the zeros in the list of values. However, with the algebra of Boole, neither of these is considered a final or adequate answer. Okay? We're moving beyond both of them, and in fact sort of unifying both of them to get a simpler, more fundamental object, the Boole polynumber associated to the Boolean function. Let's see how that goes. So now there's an important sort of transformation rule here that allows us to go from the circle sums to the ordinary sums, to replace that or in the description of a sum of products with an exclusive or. So I call this the sum of products transformation rule, and it is that for a sum of products coming from rows of a Boolean function, the circle sum and the ordinary sum may be interchanged. In other words, here is the function f that we've just talked about. Here's the expression that we just have. And I'm claiming that it's equal to the same kind of expression where the circle sums are replaced with just ordinary sums. For us, the circle sums are ors. These sums are the exclusive ors. Why is that true? Why can these things be replaced? So it's not a general fact. In general, circle sums and ordinary sums are different. But just for this particular situation, when we're talking about rows of a Boolean function table, we can perform this interchange. And it's a very important interchange to more smoothly go from a Boolean expression to an algebra of Boole polynumber. Okay, so why is it happening? So here's the main reason. Let's take, say, this term, circle sum this term. Okay, a bar, b bar, c bar, circle sum a bar, b bar, c. If we just convert that to an algebra of Boole expression using what we know about circle sum. We know we have to take the first term, we have to add the second term, and then we have to add the product of those two terms. Now have a look at the product. Okay? The product has the property that at least one of the variables is appearing both with a bar and without a bar. In this case, C. C is appearing here with a bar and here without a bar. And that's happening for at least one of the variables. Why? Because we know these correspond to distinct rows of this Boolean function. And these distinct rows are different. You look at the zeros and ones along the rows, they are different at least in one place. In that one place, in this case the C place, they will differ, and so there will be a C and a C bar. And it's the presence of this C and C bar that renders this thing 0, because C bar times C, converted to Algebra of Boole, that's 1 plus C times C, which is C plus C squared, but C squared is equal to C, and so then we have C plus C, which is 0. Okay, so that's the reason once you have a C times C bar, it's 0, so that whole thing disappears, and that's why this circle sum of these two terms is equal to the ordinary sum of those two terms. So that explains why this is equal to this, and similarly why this equals this. We still have to explain why this one can be replaced with this one. Okay, so here's that f again. Now we replace this circle sum with an ordinary sum. We replace this circle sum with an ordinary sum. What about replacing this one with just an ordinary sum? Well, if we take the circle sum of these two expressions, then we have to take this thing, ordinary plus this thing, plus their product. And what happens with their product? Well, the product is, by the distributive law, a lot of little products. So we have to take the product of this times this, plus the product of this times this, plus the product of this times this, plus the product of this times this. But each one of those products is subjected to exactly the same phenomena that we've just talked about. Take any one here and any one here. There'll be at least one input where they differ. In this case, B. B here, B bar here. So the product of these two is 0. And that happens for all of these four products. So all of those products are 0. So we do indeed get to replace the circle sums with just ordinary sums. Okay, so now it's easy to convert to a Boole polynumber, because we just have to convert these things into the Boole polynumber expressions. So a bar is 1 plus a in the algebra of Boole, 1 plus b, 1 plus c, here 1 plus a, 1 plus b, c, here 1 plus a times b, c, and here a, b, 1 plus c. Now we have to simplify this. Okay, so we could just expand and sort of collect terms and use the Boole simplifications at x plus x equals 0. But in this case, actually, often you can do things a little bit more efficiently by looking for common factors. So for example, this term here and this term here have the common factor 1 plus a times 1 plus b. In addition, there's a 1 plus c and a c. So if we pull out this common factor, what we have left is 1 plus c plus c. But that's the same as 1, because c plus c is 0. So that kind of disappears. And so the sum of these two can be immediately rewritten as just 1 plus a times 1 plus b. So then when we expand this out, we get a bc plus abc, and here we get an ab plus abc. The two abc's cancel. So we just end up with this. Then when we expand that out, we get 1 plus a plus b. The ab cancels with that ab, and we're still left with a bc. Altogether, 1 plus a plus b plus bc. That's the Boole polynumber that represents our Boolean function. We've gone from this Boolean expression thing that you would find in an electrical engineering course to this Boole polynumber. This is better. Okay? It's way better, people. Way better. Now, the second kind of expression that often appears in Boolean algebra courses is this product of sums, something like this that we saw for f. And generally speaking, these kinds of things are more difficult algebraically. So we can see that by trying to convert this to the algebra of Boole. Suppose we just take a circle sum of three things, say x, circle sum y, circle sum z, and just start by converting that into the algebra of Boole. That's a useful exercise. So here we could think about that as x circle sum y, circle sum z. Here's the expression for x circle sum y, x plus y plus xy, right, going from the OR to the exclusive ORs. We still have a circle sum z, so we have to do it again. There's the first term, there's the z, and here's the product. Okay, when you expand this all out, you have an x plus a y plus a z, you have an xy here, you have an xz here, you have a yz, and the triple product xyz. There happens to be no cancellation, we get all of these terms. So if we were going to expand this thing out naively, well, we would have to take all of these and sort of plug something like that in there. There'd be another one like this, another one like this, another one like this. So it'd be all these terms with four similar kind of expressions. We have to multiply them all together, expand out, and then simplify. That is laborious. Fortunately, we don't have to go down this road. There is a trick that allows us to circumvent this entirely. So let me explain this trick without actually going through the process of the Boolean algebra. So we'll just avoid the Boolean algebra and go directly from the table and describing the Boolean function to the Boole polynumber. And so the trick is to consider not just the function f, but also its negation 1 plus f, which we just obtained by taking the values here and interchanging zeros and ones. Algebraically, f is equal to 1 plus f. And once we've done this little trick, we see that the problem of writing an expression for f is now replaced with the problem of writing an expression for 1 plus f. But 1 plus f has ones in the places where f had zeros. So here are the rows that figured in that product of sums expression using the Boolean algebra approach. But now we can use those same rows just directly by thinking about 1 plus f and describing 1 plus f in terms of where it's equal to 1. So let's just do that. So here's 1 copied, and now 1 plus f, we're describing this Boolean function. So we're basically going back to our first situation, sum of products. This can be 1 when either there's a 1 here, or here, or here, or here. 1 here is 1 plus a, this has to be 0, times b times 1 plus c. This next one, a times 1 plus b times 1 plus c. Next one, a times 1 plus b times c. And finally the last one, a, b, c. Okay, now we simplify this. What have I done here? I think I've just multiplied this out. Okay, so 1 plus a times 1 plus c and multiply everything by b. So we get a b plus ab plus cb plus abc. Just multiplying that out. And these two terms, there's a common factor of a times 1 plus b. And so we add these two terms, the 1 plus c and the c will disappear. We'll just have a times 1 plus b, which is a plus ab. And finally the last term, abc. And so after that, we get 1, there's an a, there's a b, the ab's cancel, the abc's cancel, plus bc. It's the same answer that we got in the other method. But here what we've done, instead of concentrating on the rows where f is equal to 1, we've concentrated on the rows where f is equal to 0, which is equivalently the rows where 1 plus f is equal to 1. Okay, so it's really the same technology, just going through and seeing where something is 1, but either f or 1 plus f, depending on whether you're interested in sort of cataloging it in terms of the ones or in terms of the zeros. Okay, so if this is a big function, it has lots of ones and very few zeros, you'd rather work on the zeros because there's fewer of them, so you have to end up having fewer terms. On the other hand, if there's lots of zeros and just a few ones, then you want to concentrate on the ones. So this way we have, essentially from the Boolean algebra point of view, we've really converted a product of sums into a sum of products. But more importantly, what we've really done is we've sort of circumvented that entire Boolean algebra point of view and just found a unified way of going from a Boolean function to a Boole polynumber, either by looking at f or 1 plus f, depending which one is more appropriate. It's really just year 9 kind of algebra. Simplified, because x plus x is always 0, and because x squared is always x. Okay, so just to solidify what we've learned today, let's go through another example. Here again are 3 inputs a, b, c, and a different Boolean function called g. Value 0, 1, 0, 1, 1, 1, 0, 1. It has more 1s than it has 0s. But we'll use both methods. You can see that neither of them takes up really that much time. So, looking at the 1s, okay, where is g equal to 1? Okay, there's this row here, okay? This row corresponds to the term 1 plus a, 1 plus b, c. Next row, 1 plus a, b, c. Next one, a, 1 plus b, 1 plus c. Next one, a, 1 plus b, c. And last one, a, b, c. So this is when this thing is 1. This is 1 when either this is 1, or this is 1, or this is 1, or this is 1, or this is 1. Okay, let's simplify this. How do we do that? These two terms have a common factor of 1 plus a times c. So they can be combined just to give us a 1 plus a, c. These two terms have a common factor of a times 1 plus b. And so they simplify to a times 1 plus b, plus the last term. Expanding out, we get an a here, we get a c here, an ab from there, an ac from there, plus abc. So there's the final result. A plus c plus ab plus ac plus abc. That is the Boole polynumber associated to this Boolean function g. It is the canonical object. Let's see if we can get at the same thing by looking at the negation of g. So 1 plus g. So we write g as 1 plus 1 plus g. 1 plus g will have 1s where this one has 0. So we're now looking at the rows where g has 0s. It's a little bit simpler because there's only 3 of them now. Okay, so we have 1 plus. The first one is this one here. So that corresponds to 1 plus a, 1 plus b, 1 plus c. Here's the next one. 1 plus a, b, 1 plus c. And this last one down here, a, b, 1 plus c. When we simplify that, what's happening? There's a 1. 1 plus a, 1 plus c is common between these two. So the sum of these will be 1 plus a times 1 plus c. And this is just what it is. Now we expand. 1 plus 1 is 0. We get an a, we get a c, we get an AC, we get an AB, we get an ABC. Altogether we get A plus C plus AB plus AC plus ABC. The same thing that we did in the other case. This is the Boole polynumber for it. It's canonical. Okay, everyone gets the same answer. There's no discussion. In particular, we get to avoid a huge theoretical problem in the Boolean algebra world, which is called the SAT problem. It's a very famous problem. It's like a P equals NP kind of conundrum kind of problem. We're going to talk about that in our next video. This question about how do you tell whether this Boolean expression is equal to this Boolean expression? Okay, and how complicated is that as an algorithm or as a procedure, as a challenge? So we're going to see that SAT problem, it's not that we're going to be able to solve it, we're going to be able to circumvent it. Okay, it becomes much less important for us with this circuit analysis. In the Boole algebra story, the SAT problem just sort of drifts down the river and we wave goodbye to it. I hope you'll join me for that next time. I'm J Wildberger. Thanks for listening.